Differential pair or differential amplifier. Differential amplifier configuration is most widely used building block in analog integrated circuit design. Differential amplifier is very suitable for IC fabrication. Now, why differential amplifier is suitable for IC fabrication? Now, if we see minutely the performance of a differential pair or differential amplifier, then we can see that the performance of a differential amplifier depends on the matching between the two sides of the circuit. Now, the two sides of the circuits made of the different components, transistors, they should be matched. Matching depend on the matched transistors. So if we want to get the best performance, the matching is very important in differential amplifier. And in IC fabrication, we can easily fabricate the matched transistors. So differential amplifier is suitable for IC fabrication. One point. Another point is that if we see that the design of a differential amplifier, there are a large number of components are there with compared to single-ended amplifier where requires less number of components. Now, as in differential amplifier design, we requires large number of equipments or components, so it's very easy to fabricate large number of components within a smaller region in IC fabrication technique, so that the differential amplifier is very suitable for IC fabrication. Now, question may arise, why then differential amplifier is used instead of single-ended amplifier circuit? We can use single-ended amplifier instead of differential amplifier, but if we see the performance in differential amplifier and single-ended amplifier, we can see that the differential amplifier is less affected by the noise. So the performance is very good for differential amplifier with less noise affected. Another condition is that differential amplifier enables to bias the amplifier circuit, and it helps to couple amplifier stages. Now, in case of noise, if we see in differential amplifier, two wires are there as a two inputs and the difference will be taken. Now, as they are the wires are very physically close to each other. Now, if there is any interference there at that two terminal due to capacitive or inductive effect, then the same interference will occur at the two terminal of the differential amplifier. Now, as we differential amplifier taking the difference of two inputs, so same noise inputs will be neglected, so no noise effect will be there. So differential amplifier is well suited instead of single-ended amplifier. Now we'll discuss operation of a MOS differential amplifier with a common mode input voltage. Common mode input voltage, that means the input of the two terminal are same. Voltage input of the two terminal are same. Okay. The circuit diagram basic MOS differential amplifier. Now this is the circuit diagram of basic MOS differential pair configuration. Now here two transistor Q1 and Q2 is working. They are matched. Q1 connected with a resistor RD. Q1 drain terminal is connected to RD with a supply VDD. Q2 transistor also connected to VDD through a RD transistor. VD1 is the output. We are getting VD1 across here voltage and drain voltage for Q2 VD2. Gate potential is Vg1 connected to Q1 and gate potential Vg2 is connected to Q2 NMOS transistor. The source of these Q1 and Q2 transistors both are common and connected to a constant current source I. Now, as both transistors are matched and assuming both transistors are operating in saturation. Now when the input are amplifier input are common mode input voltage. So when Vg1 equals to Vg2, now take Vg1 equals to Vg2 equals to Vcm, that is your common potential Vcm. So instead of Vg2 we can write Vcm or Vg. Vg1 equals to Vg2 equals to Vcm, common voltage applied across the gate of transistor Q1 and at gate of transistor Q2. As both transistors are matched and the same potential is applied across the gate terminal and the source of both Q1 and Q2 are connected to a constant current source, the current is passing, that is I. Now I should be equals to ID1 plus ID2. Now as both transistors are matched and their threshold voltage is same and gate potential are same, so ID1 should be equal to ID2. So we can write that equals to I by 2. Okay. Now as both transistors are working in saturation, so I can write ID1 equals to I by 2 equals to half into Kn dash W by L into VGS minus VT whole square. Kn dash equals to mu NC ox. Okay. Now VGS minus VT equals to V overdrive voltage then we can write I by 2 equals to Kn dash by 2 W by L V over drive square. From there we can find out V over drive equals to I by Kn dash W by L root over. Now if we want to find out the source voltage Vs at that point Vs, then we can write Vs should be Vs equals to the potential applied that VCM at gate terminal minus the potential difference between gate and source minus VGS. Now from here we can write also VGS equals to V over drive plus VT, that we can write VT plus V over drive equals to root over I by Kn dash W by L. Now if we want to find out the potential VD1 and VD2, then VD1 equals to, we can write the supply is here VDD minus the potential drop at this RD, that how much current is passing through this RD, that is ID1. ID1 equals to I by 2, so I by 2 into RD. For VD2, that also VDD minus the potential drop at that point, that is the current passing through RD is I by 2 into RD. Okay. Now if we want to find out the operating range of a common mode input voltage differential amplifier, then common voltage range, in which range VCM, what will be the VCM range within that the differential amplifier configuration will work properly. So we have assumed that the transistors are working in saturation region. So in saturation region condition is that, so you can write current passing through this transistor should follow the condition that VDS should be greater than or equals to VGS minus VT. Now what will be the maximum voltage for this VCM? Now we have to find out the range of VCM, that means the maximum VCM and minimum VCM. So VCM will be maximum when VCM nothing but VCM equals to VG. Now VG, when VG is maximum, then VCM is maximum. For that, VGS should be high enough. Now if this condition should satisfy, then if we increase VGS from condition of VDS greater than VGS minus VT, now if we increase VGS, that means if we increase VG, then at some point the condition will arise when VDS should be equal to VGS minus VT. Okay, so if we write that, then VDS is VD minus VS equals to VG minus VS plus VT. If you cancel out VS, then VD equals to VG plus VT. That's the condition. So VD is nothing but the potential at VD1. So VD1 equals to VG plus VT. So that's the maximum voltage. So VMS, that's the maximum. So VG is max. So VG is max. This is max. So this max is nothing but VCM. So you can write VCM max equals to VD1 minus VT. VD1 equals to, we have seen that VD1 equals to VDD minus current passing through drop, VDD minus drop across this RD, that is I by 2 into RD minus VT. Okay, sorry, VCM, this is VGS minus VT. VGS minus VT, this is negative minus, this is negative, this is negative. So this should be positive. So this is positive. So VCM max is equals to VT plus VDD minus I by 2 RD. Okay. Now what will be the minimum of the input VCM, minimum range? So for minimum, this S should be, we have to find out the S. So if we reduce down this VCM and VGS is the VCM minus VS, that VS should be the potential minimum, required minimum voltage to assume that the current source I requires. This potential is minimum potential required to operate the ideal current source perfectly. So the potential drop at this is VCS. So if this is Vs, that this potential is, and here the potential drop across here is Vcs. Then if we take this closed loop, if we take this closed loop, then if we apply KVL, then we can write VCM equals to VGS plus VCS, the potential drop across here, minus of VSS. So that's the minimum VCM requires for that. So you can write VCM minimum equals to VGS, that is nothing but, in case of, we know previously, V overdrive equals to VGS minus VT. So VGS equals to V overdrive plus VT. So we know V overdrive equals to VGS minus VT. So VGS equals to V overdrive plus VT. So if we put here instead of VGS, so you can write V overdrive plus VT plus VCS minus VSS. That's the minimum voltage required to operate perfectly. Minimum voltage required to operate the differential amplifier perfectly. So the range of VCM is, minimum VCM is this, and maximum VCM is this.